Let's look at another example of the momentum equation. We have the nozzle. A jet of water emerged from the nozzle. Okay. We have two situations. One situation is that if the velocity is uniformly distributed, okay, we just call it like a uniform velocity, v across the whole jet area. Remember, like the last example, and we're just going to see what is the momentum flow rate. Okay. And if the velocity is not uniformly distributed, and if the velocity over the central half of the jet in area of the a second, so half of the area, the central half, the velocity is a 1.5 times velocity v, and the velocity over the outer half, so the outer half is the velocity is a half v, or 0.5 v. So for the second case, we're just going to need to calculate the momentum of the flow rate. Okay. So we know the equations here, and the momentum, we know that the momentum on the right-hand side, the difference of the momentum we calculated in the momentum equation, but the momentum normally is like a rho qv. Okay, so with that assumptions, we know the momentum is mass times velocity, or momentum flow rate is like a mass of the flow times velocity, or rho qv, or as we know, like a q is equal to av. You can just write the AQ substitute here. So we're just going to have like a rho Q, rho AV squared. Okay, we substitute here with the AV, and that's the equation. So let's go with the calculation here. So this is like for section A. For section B, so this is actually for everything based on the parameters. This is the answer for section A, is like a rho A V squared, because the velocity is a V. Okay, but for section B, it says that the area, the half of the area has got a velocity of 1.5, and half of the outer area, the velocity is half v. Okay, we're just gonna write everything here. Rho, okay, rho a is half of the a, okay, times velocity is 1.5 v, all of them raised to the power 2. This is the half momentum, plus the next half is plus rho half a times half v squared. Okay, so if you're just going to raise this on to the power 2 and times half and add it up to this kind of like the first term, we're just going to get 1.125 rho a v squared, okay, plus 0.125 rho a v squared. So the result is 1.25 rho a v squared. Okay, the answer is simple as that. So we're just going to conclude that if comparing this equation in section B compared to equation in section A, we can say we have like a 25% increase in the rate of the flow of the momentum, despite the fact that the flow rate or the flow of the momentum is the same. Why? So let's calculate this one. If you know that the flow rate of Q is equal to VA, okay, for the and it is like a sum of the whole two types of the like a flow discharge. So for the inner side, it's like the 0.5 A, okay, half of the area times the velocity was 1.5 V plus 0.5 A times 0.5 velocity, because it's like the velocity in the outer area is like the half V. So altogether, the first term is like a 0.75 AV, and the second term is 0.25 AV. So the sum of these two is equal to AV. Okay, is it like a 3/4 and it's like 1/4? Altogether is like a 1 AV. So you can see here the discharge, the flow discharge is exactly the same, or the quantity of the flow is the same. However, the momentum for the situation that we have like this kind of like the distribution is uneven or non-uniform distribution, is like a 25% higher than section A. Okay, that's another example for the momentum.